Hi, hello. Welcome to section number 9. Next to last section, only one left. Scanning the QR code. The question for today, what's your coffee, tea, boba order? I'm a classic, just plain hot latte or cappuccino. I want to see, can they get the microphone in the milk? Can they get all the little microphone? Even in hot weather, I'm a hot drink girl. Occasionally I'll do an iced latte, I'll go crazy. I used to be a vanilla latte girl for a long time, but so game plan for today. We're gonna spend about an hour doing some content, and in the last 30 minutes, we are gonna do how to study reactions part 3, and we are going to do a hard synthesis together from the extra challenge problems. It's probably the hardest synthesis you've seen so far, or like one of the more challenging ones. So again, we have kind of content for the first hour. Last 30 minutes, we do other stuff. I had to bump something from this section. Something had to be bumped. The thing I bumped, aromaticity. I bumped aromaticity because it's not that hard. It's kind of an isolated skill. But I didn't leave you in the lurch. There's a QR code for a video. You can watch a video and I talk about it. I talk the little electron hamster wheel. Makes a bond. Oh, I'm so much more stable now. This thing doesn't want to exist. She bends. She aggressively doesn't want to exist, which, sometimes relatable. But going back over here, what are we going to actually talk about in the first hour for content? We're going to start off with radicals, which was in lecture 8, which you're definitely going to have a mechanism question on for exam 2 or the final, one or the other. Then we're going to talk about EAS reactions. In particular, we're going to talk about Friedel-Crafts for a little while. That's where you saw me doing my homework at the last minute, which I'm still doing. So we'll see how that goes. We'll try it out. And then finally, we are going to talk about directing effects, which is some of the kind of theory involved with the EAS reactions. Are there any big logistical questions before we jump into section proper? Radicals. They're out here doing their thing. One electron, not a lone pair, a lone single. Crazy. Anytime we have a radical, we have a deficiency of electrons. Electrons like to have two, orbitals like to have 2 electrons. Radical is only 1 electron in the orbital. And so because we have a deficiency of electrons, it's kind of behaving like a carbocation in a lot of ways. So the same trend for what makes carbocations more stable also works for describing what makes radicals more stable. So our secondary and tertiary are more stabilized because of hyperconjugation. And then if we have it next to a double bond, we can do resonance. The resonance looks a little weird now because we have 3 arrows. So we're going to make our double bond here with 1 arrow. And we're doing our single fish hooks to show 1 electron moving. And it's like a boop. And then we're going to break up the pi bond. 1 electron's going to go boop and make a pi bond on the other side. And the other electron's going to go on the far side. And so what we get is a resonance structure where now our double bond's here and our dot's over here. I don't know why radical arrows to me are very like boop, like a little boop. So I'm going to be saying boop a lot in this first section, so sorry. But let's talk about our general reaction. We are only really teaching you one Platonic ideal reaction here for radicals, and that is the radical bromination. So normally, if you did an alkene with HBr, that's one of our acid additions. It's going to add an H and a Br. It's going to add it Markovnikov. It's going to put the bromine right here. But however, we saw if we sprinkle in this ROOR, which is peroxide, and we do it in the presence of this delta, which is either heat, or HV, which means UV light, one of these conditions, then we actually get our anti-Markovnikov product here, our bromine added to the less electronegative. I have an FYI box here. I'm not going to go into a ton of it, but ROOR is our abbreviation here for something that has an unstable bond between 2 electronegative elements. These bonds, when exposed to the heat or UV light, can do something called homolyzing. And when it homolyzes, it basically splits so that each partner gets 1 electron. And that's going to start off all of our radical things. We tend to call this molecule a radical initiator. And there are lots of examples. One of them is called BPO. One of them is NBS. You don't need to know these in particular, but you need to be on the lookout for these bonds that can homolyze pretty easily. And again, in general, we will use ROOR. If you need to supply something on like an arrow, you put ROOR. Roar. So let's talk about the mechanism of this. Anytime we have a radical mechanism, there are 3 stages to it, a 3-act structure. First act is initiation. How do we go from no radicals to radicals? And these are your gimme points on the radical mechanism, if they have them. Like sometimes we don't have a ROOR situation and it's within the same molecule. But if we have them, these are like 5 points that you should have locked and loaded. You should be able to draw this in like 7 seconds. This should be a vine. What happens is you do a homolytic cleavage, homo, aunt situation, homolytic cleavage here of your sigma bond, and you make 2 RO dots. Then RO dot interacts with our HBr. It is going to break this sigma bond, so the RO takes the H, makes an alcohol, and then we get one dotty bromo boy. And dotty bromo boy is the one that's going to interact with our reagent, with our alkane. So, going from no radicals to radicals. Then we get to propagation. Propagation is, it's messy, and it's going to continue to be messy. Start with radicals, end with radicals. So, this is where we interact with our alkene for the first time. Alkene comes along, interacts with dotty boy. 1 electron in the pi bond goes boop, boop. They make a little bond here. And then the other electron gets pushed over here. Now, hypothetically, if we are adding a bromine and a dot, we could do it the other way. We could do dot over here, bromine over here. But why is this way preferred? Secondary versus primary. Secondary is more stable. That's exactly it. So here we are forming our more stable radical, just like for carbocations we form a more stable carbocation. And then the 2 things we need to add are an H and a Br. We've added the Br. So we are going to get another equivalent of HBr here, and we are going to grab an H from it. When we do that, we make our product. Our product is the anti-Markovnikov addition here, but also we generate another bromo boy, you know? Started with radicals, ended with radicals. Mess produces mess. Now, one thing that we should think about here, why did we do anti-Markovnikov? Like, I know we just did this mechanism, but like, why was this anti-Markovnikov versus HBr without radicals is Markovnikov? Let's compare contrast. What is the thing that we are adding in the first step with non-radical bromination? We're adding the H first. We're adding an acid and making a carbocation. What's the thing that we're adding first in radical bromination? The Br. In both cases, whatever we add first gets put on the end. Why? To make the more stable radical or carbocation. Exactly. I love y'all's participation. I appreciate you. So, in both cases, we are making the more stable radical or carbocation. The only difference is what's the first thing that's added. When we are in a radical setting, bromo boy is our reactive girl. When we are in our non-radical setting, it's acid time. Great. So then we're done. We have our product, but more is going on. You know, after the climax of the movie, they have to wrap it all up, make you feel good at the end of the day. We have termination. So termination goes from radicals to no radicals. So you could have 2 bromo boys bump into each other. Now they're bros. You could have an intermediate with a radical bump into another bromo boy, and you have a side product where there's a double bromination. There are lots of ways this can happen. It's really annoying. We never really ask you about this because it's boring and we've already generated our product at this point. We always want you to show initiation and propagation. We never ask you to do termination. Just know that there is a third part of the movie that we're going to skip. So this is the Platonic ideal. This is like nothing weird happening, simple. Any questions on the general framework here before we make it messy? So, again, this is the standard reaction. You can do this in a box problem or potentially a synthesis if it's really, really straightforward. If there are any complicating factors, you want to avoid this for synthesis because you don't want to be thinking about full curved error mechanisms, you don't want to get side products, bad yields, all this. So generally only use this for a line reaction or synthesis if there's nothing that can go wrong. But the other thing is, in this propagation land, in the mess begets mess, you can do some crazy stuff. I was gonna say a curse word. Y'all are adults. I can say crazy shit. So, namely, we can open a ring or we can form a ring. So let's see some examples that do that. So this is Skill Builder, page 18. Let's talk about a general strategy for doing these mechanisms for radicals, which you are definitely going to have either on exam 2 or the final. So whatever you do, number your carbons. You might think that you don't need to. You need to, especially when we give you a hard one on the test. So I'm going to number these 1, 2, 3, 4, 5, 6, 7. And when I do this, I need to map this onto the products. It's not totally obvious, but I'm like, this is the longest straight chain. There's a long straight chain over here. So I'm guessing that this one over here is either 1 or 7. Do you buy that? Okay. Knowing the Platonic ideal mechanism, the first time that your alkene interacts with any reagent, it adds a bromine to the less substituted side of the alkene. Based on that, where this bromine is, if that's the first thing that's added, I think that carbon 1 is right here. Do you buy that? First thing is bromines added to the less substituted side of the alkene over here. So I'm thinking that this is 1, 2, 3, 4, 5, 6, 7. We've numbered. Now, this is the core part of the strategy. Once you've done your numbering, you need to make a list of bonds that you need to make and bonds that you need to break in this reaction. I will not be supplying any of them, so you tell me.
You need to make a 3-6 bond.
Great. Or break a 3-6 bond, right?
Oh, yeah, sorry.
So 3 and 6 are connected over here. They are not connected over here. What else? So we need to make a pi 2, 3. And while we're on double bonds, don't we also need to break a pi bond? 1, 2. Great.
You have to make a bond with bromine.
Yeah. 1 bromine. Okay. And this is the kind of obvious ones that we see here. But there is always kind of a sneaky thing that you need to be watching out for when you're doing your make and break list. And that is watching out for hidden hydrogens. Remember, in HBr, we added an H and a Br, but why does that hydrogen hide? Well, we typically just don't draw it in our skeletal structures. So we've probably added a hydrogen here. Where? I mean, we could do okay, there are 2 here, there are 2 here, there's 1 here, there's 1 here. But generally speaking, focus on places where you've broken a bond. 3 and 6 each have 1 hydrogen here. 6 has a new hydrogen. Hidden hydrogen. I wish I had the sound effect that's like do-do-do-do-do-do-do-do, like ookie spooky. So we need to make a 6 hydrogen bond. We have our make and break list. Do y'all feel good about it so far? Okay. The last thing is observe the radical mechanism norms. Do your normal initiation. Start off normal, and then use your make and break list to figure out what happens next. So the initiation, I'm going to blow through because it is something that you just memorize and you bust out like a party trick. Next time that you're at a fun little party, be like, oh, you want to see me do radical bromination? I can do the initiation in 5 seconds. Ooh. Our dot comes along with HBr. We do a boop, and a boop, and we make ROH plus BR dot. Then we start our propagation. You don't have to label them initiation, propagation. I just think it's helpful to be we're done with that. So now we know that we always start off BR dot interacting with the alkene. So that's kind of our first step. Let's do it. Kiss, and then the dot moves over. Cool. So, which of my goals have I accomplished at this point?
You've broken the 1-2 pi bond and added the BR.
Great. Okay. So now that we've done this, we've done the things that we can just directly reproduce from the Platonic ideal mechanism. So now, my reactive part of my molecule is at 2. So I look, what goals do I have that are connected to 2? I need to make the 2,3 pi bond. But if I make a pi bond, I need to get electrons from somewhere else. Well, typically, we can only get electrons from breaking something. So oftentimes, you're going to be doing 2 goals at the same time. So here, because we're reactive at 2 with a radical, we're going to make our 2,3 pi bond, and we're going to get the electrons from it from breaking the 3,6 sigma bond. So let's do it. So 1 electron goes in here. 1 electron from the 3,6 bond goes in, makes the pi bond. The other one, we put a dot on 6. At this point, we've done all of our goals except for the hydrogen. And so we add the hydrogen the same way that we did in a normal like HBr mech. By normal HBr radical bromination mech. So these two boop together, and then we get to our product. And we've generated another Br dot. We don't care about the termination. Questions about this process so far? Let's get a little stranger. Challenge problem 7. Radicals. Looking crazy. What do we notice? These rings are the same. I am speaking to the beat of the song. Woo, woo, woo. What else do we notice? No 3-membered ring. Woo, woo. What else do we notice? No 5-membered ring. Instead, we have a 6-membered ring and a carbonyl. We made a carbonyl. Wow, I've never tried that before. That's crazy. But yeah, this one looks way crazier, right? What is our tip-off that this is a radical mechanism?
Oh, the HV.
The HV is really the thing that's the more obvious thing to me. So our tip-offs are if we have ROR, that tells us we're doing this. If we have HV, if we have a delta, typically, that's the tip-off. But then we know that we need a bond that we can homolyze, or homolyze. I now don't know how to pronounce it. Yeah, Han.
I thought I remember them saying that radicals would rather form 5-membered rings than 6-membered rings. Was that not?
Maybe.
So why are we going from a 5 to a 6?
I don't know. If I'm so honest,
Okay.
a lot of this, and I think that students get really tripped up on radical mechanisms because I think that y'all are trying to understand it from like a why does it happen? And it's literally like nature did this and we're just trying to see can we like show how it did it? The why is a much more of like thermodynamics question. Like it's a great thing to think about, but honestly there are so many factors that even with a chemistry degree and 10 years of OChem, I couldn't tell you.
Okay.
Yeah.
So it can just go either way.
Yeah,
Okay.
like there's no way. This question would be fully impossible if we did this.
Yeah.
Yeah.
Okay.
I mean, if I had to spitball here, this bond's not very stable. We're breaking it. We're getting rid of a 3-membered ring. And so this, by getting rid of this, it's not so much about the 5-membered ring. It's about breaking that unstable bond.
Yeah.
We make this pi bond, which is going to have like a higher delta H that we can use. And then the 6-membered ring minimizes like conformational, like bumping in.
Yeah. Okay.
That's just off the dome. So we're going to do the process again. This all looks the same. So I'm going to start my numbering. 1, 2, 3, 4, 5. I'm just numbering carbons. I'm pretty sure 1's still up here, right? 1's still up here. 2's probably still here. Would it make sense for this to be 3? Well, 3 was connected to an O, so maybe, sure. And then between these 4 and 5, those are symmetric over here. So does it matter which order we do? No. So I'm just going to do 4, 5. So now we do the hard part. What's our make-break list?
The sigma NO. We're gonna have to break.
Say one more time.
Sigma NO.
Yeah, so we're going to break NO. What else?
You're gonna make a pi on
Yeah, pi 3o.
You break?
What?
Break 5-3?
Yeah. Wow. Maybe I do have ADHD. Because in my head I said pi 3o. Where in the digits of pi do you have a 3 followed by an o? And I was like 3141592653589. Like I was like going through it while y'all were thinking, and I was like, I didn't get to it for a while. But okay, and then other bonds to make. 5N. Okay. Do we have hidden hydrogens? Do we have another molecule that we could have gotten hydrogens from? No. So we don't have hidden hydrogens. So let's start. Step 1, homolysis. Maybe I do have ADHD. This is crazy because I said homolysis. The homo lied, sis. What am I doing? I think I'm just sleep deprived. I think that's really it. I'm just going to call this R. On your P sets, you actually have to write it. But I get to be lazy because... Thank you. Thank you. Wow. I wasn't going to say it, but I'm really glad that you did. So with this, we broke the NO bond. Okay. So now, what do you want to do as our next goal? We can either do stuff with the N or the O. So do you want to try and make the pi bond first, or do you want to do the nitrogen 5 bond first? Pi bond? Any pi bond? I don't know. To me, that just seems a little bit easier, mostly just because 5 right now, she's fully just minding her business. And so part of me is like, why would she go and attack? She might, but like, I'm like, this oxygen's up to no good. She wants the carbonyl. So if we make our 3O, we need to get electrons from breaking something, right? So let's break the 5-3, make the 3O. That sounds like nonsense, but this was 3, 4, 5. So 1 electron from the O goes down to make the double bond, and we're breaking the 5-3, so 1 electron goes in, makes the pi bond. The other electron, 3-5 bond, goes onto 5. Okay, so now we've accomplished 2 of our goals. Hey, we only have 1 goal left. Oh. Boop, boop. And here, we're at our product. 1, 2, 3, 4, 5, and the nitrogen makes 6 for a 6-membered ring. So this really scary looking radical question was only 3 steps. And one of them was literally just like homolysis. Yeah.
In a radical question, do we, like, I don't know how to word this out, but do we only do radicals, or will there be mixes of like radicals and non-
Only radicals in a radical question.
Okay.
Yeah.
And do we ever have a HB with anything else, or do we always see it?
Not for y'all.
Okay, good.
Yeah. There are these cool electrocyclic reactions that you can learn in Chem 30. But yeah, for y'all, this is the only one. I don't know if I could find it really quick.
No, it was just asking.
No. You're good. I'm talking about something else. Radical mix are used in FAD chemistry. And so, like an example of an FAD mechanism with radicals is... Oh, what is all this? This is kind of what it looks like before I typeset things. It's like handwritten. So yeah, like FAD starts by doing 2 electron chemistry, and then it does 1 electron chemistry here and does some resonance and things like that. So like it pops up in cool places in biology. And also like if you might have heard of like, like antioxidants are good for you, right? Antioxidants are things that get rid of reactive oxygen species, which are oxygens with radicals. The reactive oxygen species are radical oxygens. So, like, it has fun, like, biological relevance. I'm just out here fully in a different plane of existence. Are there any questions on radicals?
What's the likelihood that we have a radical question on the second exam?
I have no idea. I'm going to write a bunch of questions, like box problems, synthesis, mechanisms, and I'm honestly going to write probably the final exam and exam 2, all the questions, and be like, Logan, pick which ones you want to do. Yeah.
Is the reason why you reacted with the oxygen instead of the nitrogen was because it's oxygen's more electronegative?
To be so honest, I don't have a strong reason for why. We probably could have done it the other way too, and I think that would have been a valid, like, gets the points kind of way. Yeah, I don't have a strong reason for why we did the O version. Maybe the only other thing being like these are closer, and because these are so close to each other, that might be faster than like if you just interacted here and you did like the opposite one would be radical on 3, this connects over here to the nitrogen. There's an element of these would have to bump into each other that I think makes it slower. That's honestly probably my go-to explanation for it. Yeah.
You got me thinking about digits of pi now.
Yeah, it'll mess you up. The time has come for our last reaction family of exam 2, electrophilic aromatic substitutions. What are we trying to do? We're trying to put things on a benzene. We're trying to add chemical groups to a benzene. But benzene, is she very reactive? No. Why? Resonance, aromaticity. She's super. It's going to keep going. That's crazy. She is super, super stable, so she doesn't want to react. But also, duality. She has a lot of electrons, right? The electrons are in those pi bonds. They're going round and round and round. She has electrons. She just doesn't want to use them. She says, "I'm not a fighter." So, benzene's likely a nucleophile, but it's really bad at being a nucleophile. So that's our barrier. So what we have to do is we have to generate not just good electrophiles, not just great electrophiles, excellent electrophiles. We need the electrophiles, your favorite electrophile's favorite electrophile. We need electrophiles that are not shelf stable, that will like fall apart. And so we make electrophiles from combining multiple reagents, and then the electron only the electrophile, the really, really great one, only appears in that mixture. We call it generating it in situ, and think like it's in the middle of the situation, kind of. So once we have our really amazing electrophile, the EAS mechanism is the same for all of them, and it's super easy. 2 steps. 1, our men nucleophile benzene goes and attacks the great electrophile. But when we do that, we disrupt the force. We disturb aromaticity. So something has a carbocation now, and then we've added our electrophile, but the site that we added the electrophile still has a hydrogen on it. So step 1 is adding our good electrophile. Step 2 is we're going to restore aromaticity. And we restore aromaticity through this E1-like mechanism here, where we deprotonate the hydrogen, fold back in, make a double bond. So add the electrophile, restore aromaticity. It happens with each EAS reaction. You're going to get sick of it. Now, with the EAS mechanisms, you're responsible for 6, and they're kind of grouped into 3 subfamilies. The first is halogenation, where we add a bromine or a chlorine. The second is deactivating acids, where we add a nitro group or a sulfonic acid group. And the third are Friedel-Crafts, where we add carbons. So with these, because that good electrophile is so important, And because it's only formed as the mixture of a few reagents, when you are studying your Friedel-Crafts reactions, when you are studying your EAS reactions, you not only need to think about memorizing what these are, the reagents in the arrow, you also need to be memorizing what is the good electrophile species here. So with these, you can't, on the exam, you can't just poof these good electrophiles out of thin air. You have to make them from the reagents, which is annoying. But then if you didn't, all these mechanisms would be exactly the same. They would just be those same 2 AAS steps. So the only thing that makes them different is how to make the electrophile. So I have a little box here that goes through some of them. A lot of them use Lewis acids to kind of coordinate and make better leaving groups. But I'm not really going to talk about these because these are just something for you to kind of study. Yeah. Cool. So now we're going to talk about Friedel-Crafts, and if you are looking at the notes, you might notice that they are blank, and it is because I've been trying to workshop how I talk about Friedel-Crafts. I've tried to pre-write some of it, and I've gotten some of it. So I'm going to talk through what I've written, and then I'm going to talk much slower and write some things as well. And then hopefully by 1 p.m., you know, I've shown up for my job. I've done my due diligence and duty. I'm really failing the youth out here. But let's talk in particular about this Friedel-Crafts family because this is the one that has the most kind of thinking involved with it. So our core question is how do we add carbons to a benzene ring? There are 2 main ways that we can do it. One way that we can do it is with an alkyl halide. We can add carbons and just a normal alkyl group. This is kind of the most straightforward way of thinking about it. We call this Friedel-Crafts alkylation. We're only adding carbons. If instead we use an acid chloride as our reagent, both of these with AlCl3, then acid chlorides add carbons and a carbonyl here. This we can call a couple of things. One, we can call it an acyl group. An acyl group is a name for a functional group of a carbonyl with something on it. So all of our CAD reactions are often called acyl transfer reactions because you're transferring, okay, I had an OH, now I had an NH2, okay, now I have an OR. I'm transferring this acyl group onto different things. That's one way of thinking about it. It's also sometimes called an aryl ketone because this is an arene ring and we have a ketone right next to it, an aryl ketone. So this we call Friedel-Crafts acylation, where we add the carbons with a carbonyl. Now, for each of these, we need excellent carbon electrophiles. So let's start off with Friedel-Crafts acylation because it's a little bit more straightforward. In acylation, your acid chloride associates with AlCl3, that Lewis acid. And now this Cl-AlCl3 becomes a really excellent leaving group. So we're going to do this fun little reach around, push down, kick off. And the good electrophile that we make here is called the acylium ion. Ooh. I call her Super Carbonyl. And again, once I typeset her, she's going to have a Supergirl, Superman cape behind her. And she's going to be like, I'm your favorite carbonyl's favorite carbonyl. At this point, the nucleophile, which is just a benzene ring, can attack it just like a normal carbonyl, push up. And after those standard EAS steps, we've added on our acyl group. So the only hard part is making this acylium. It's a really robust reaction. Our really only limitation of it is you need 2 or more carbons. You can't just add 1 carbon and do this little girl. This is the formal chloride. And it's because she's going to fall apart into HCl and carbon monoxide gas. And so she's not going to work. So that's Friedel-Crafts acylation. Alkylation, though. We basically have 3 different ways of thinking about the mechanism here, and that's kind of what starts to get weird and a little bit more nuanced. So first type is if we have our alkyl halide, where our alkyl halide is methyl or primary, we can do kind of an SN2-like mechanism. We're going to associate, get that good leaving group, and then the benzene ring is going to do an SN2 attack on here. And again, I'm just using new because I don't want to keep writing out the benzene. So we do an SN2 attack, we add our alkyl group after those EAS steps. This is great for adding a methyl or an ethyl. That seems pretty straightforward, SN2. But you can also do SN1. So if our alkyl halide is secondary or tertiary, we're going to do something that's more SN1-like. That's kind of weird, right? Like normally we think secondary goes SN2, but here, like secondary, the real reality is it's somewhere in between SN1 and SN2. And it's more helpful for y'all to think of secondary doing SN1 and thinking about rearrangements. So we're going to treat it like it's a rearrangement. We get that good leaving group leaves, and then our excellent carbon electrophile is a carbocation. Over here for SN2, we just made an even better alkyl halide. We activated it by making the leaving group like really want to leave. So we attack the carbocation, we're good. So we can add like a tert-butyl group, we can add an isopropyl group here, carbocations. The last type is we can do it from an alkene and acid. And this is an alkene and acid. First step, you add the H, you make a carbocation. And so this is the same exact idea here. So the same ones that you could have done with a carbocation with a alkyl halide, you can do with alkenes. So now we get to the part where I have to start writing. So I'm so sorry. So Friedel cross alkylation, lots of options, and in organic chemistry we don't like lots of options. We have some issues with her. One is the idea of over-alkylation. So if we are doing our benzene here with like methyl, chlorine, AlCl3, we are going to get her. We are also going to get her. Anyone know who else we're going to get? Meg the Stallion's her. And you want to know who else we're going to get? You won't guess. Her. And them. Be mindful of pronouns. So this idea that when we put an alkyl group on our benzene, we actually make it more activated, so it's going to want to react more. And it can just keep on adding methyl groups here. And so we get like a big mixture here. So that's one issue. Another issue is, let's say you were trying to do this Friedel-Crafts alkylation. Well, we know this is secondary, so is it going to be SN1-like or SN2-like? SN1-like, so let's draw out what that carbocation is. Secondary carbocation, is this going to rearrange? It's next to a tertiary carbon. So what we're going to get is a carbocation over here. So our product is not going to be the connection. I'll do kind of in red here. We do not get just like plugging in our benzene where the chlorine was. Instead, what we get is this rearrangement version. That looks like this. So attacking from where that carbocation was. So that's one issue, always carbocations. But then even more than that, this is something Logan didn't talk about, and this one you're technically not going to be tested on, but it's like part of the kind of secret sauce of like what's going on here, is if you are using primary alkyl halides with 3+ carbons. So like let's look at propyl chlorine with AlCl3. You are going to get her, right? She is the expected product. But you are also going to be getting her. Unexpected. What's happening here? You are not responsible for this mechanism, but to give you an idea of it, you've done your AlCl3 association here, plus minus, and yeah, it can do an SN2-like attack here, but it can also do this move where you have a rearrangement and the leaving group leaves, which you saw a little bit on one of the problem sets. And when that happens, we get this carbocation. So we get rearrangements even before we're doing like an SN1. That's crazy. And so because we have all of these issues, we need a way of adding carbons that avoids all of this. Our solution for doing that is to do an acylation and then erase the carbonyl. So general plan, we are going to go, and if we wanted to get to a product where we only get this, the first thing that we are going to do is we are going to add our carbons via an acylation. So we are going to use over here the acyl chloride version with AlCl3. And then how do we get rid of a body? How do we dispose of a carbonyl? Well, let's reverse engineer. No body, no functional group, that's an alkane. What is a reaction that you've learned that makes alkanes? There's only one.
The H2 thing.
Yeah, so if we have an alkene, we can turn that into an alkane with H2 palladium on carbon. Okay, we need to get to an alkene then. Well, alkenes are made generally via elimination, right? Okay. Well, we're at the wrong oxidation level. Why don't we start off by first step, reduce. And when we do that, we're going to get to an alcohol. Now, how do we get from an alcohol to an alkene?
You need to make it a better group.
That's one way. Can you do it in a direct step? Alcohol to an alkene. You conk it. So we can do this 3-part strategy here that adds our carbons. It avoids any rearrangement. We don't have a carbocation. We are not likely to over-alkylate. And also we're not doing this like weird rearrangement thing. Acylation reduction is great. It just takes more steps. In a normal OChem class, you learn reactions that do all of this in one step. And they are some of my favorite reactions, which is why I wanted to talk about it a little bit. I call that family of reactions Women Are Powerful. They all have like fierce names. They all are like, yeah, like one of them, it turns it into this, which what functional group does this look like? Acetal. This is a thioacetal. So literally you use HSSH, H+, just like you would for an acetal. And then the fierce step, H2 with this catalyst called rainy nickel. And all it does is go shh, erases it away. I love it. The other one's like the Wolff-Kishner and the Clemenson, like really cool chemistry. But this is the big idea I wanted to talk about with you of like, hey, we have some idiosyncrasies. We have some nuance going on with alkylation and acylation in Friedel-Crafts land. And so if you're doing Friedel-Crafts, know that you have to think a little bit more than if you do any of the others. Questions on her?
Do you have any
Yeah.
adding the heads to?
No. That's a great question. I mean, actually, so I have it's going to take us off time a little bit, but there are 2 questions I think are really cool. One question is, how do we get that on a benzene? And maybe another question would be, how do we get that on a benzene? So firstly with this one, can we use Friedel-Crafts acylation? Well, to see that, if we did like acylation plus reduction, can we have had a carbonyl here?
This ain't Texas.
No. Oh, I didn't clip it. So, yeah, we can't do acylation because that carbon would have 5 bonds, right? So that doesn't work. Can we do alkylation? No, because if we look at it, we have a carbocation here. Is that carbocation going to be stable or is it going to rearrange? It'll rearrange. So how could we do it? You're going to hate this. So,
Sorry, why would it rearrange if either way you get a tertiary?
because it's secondary here.
Oh,
No. It's tertiary once it's connected, but before that attack happens, it's going to rearrange. So what we can do is, let's go ahead and add all of these carbons with an acylation. And again, I'm thinking through like hard things. This is like a little bit beyond the scope, and y'all are indulging me on my flight of fancy. Here, now that we're here, how can we add one more carbon to this? We could do Grignard, then we could, if we do a Grignard of a methyl, then we have an OH here, and then we could do alkene, and then H2 palladium on carbon, but there's a much faster way. And it's cool. What's another way to make a carbon-carbon bond that we learned last lecture section?
oh.
It mogs all the other reactions. Say again? The Wittig. So we can use a Wittig ylid here with one carbon, and that's going to make an alkene, and then we can use H2 palladium on carbon. So that one works. Another one here, I'm going to think backwards for us. I think that we can only do this by adding more carbons and then removing some carbons, right? So what if we did an alkene and then we did ozonolysis? That would break this bond in half and put a carbonyl in its place, right? So then our question becomes, okay, how do we add an alkene? Can I do that directly via Friedel-Crafts alkylation or acylation? Cool. No, we can't do this as a carbocation. It's a really unstable carbocation. And so we need to do this from, let's say, an alcohol, which we can do from a carbonyl, which we can do from this FeCl with AlCl3 and benzene. So that's kind of a way to do it. But this is us thinking about really complicated synthesis things, synthesis goals. And this kind of thinking can only really happen once we've studied all of our reactions, once we've internalized this. So if the last 5 minutes we're like, ah, that's fine. That's totally fine. Questions on this? Mm-hmm.
Could you feasibly also do that by going straight from the ketone to, no, because you can't go from, never mind.
All good. But, okay. I went on tangents here. Thank you for indulging me. Let's pretend this didn't happen. Directing effects. So, story time. I remember when I was learning these reactions, these EAS reactions for the first time. It was the spring of 2016. Wow, it's been a decade. That's crazy. I was a senior in high school. I was at the local coffee shop, Jittery Joe's. I arrived at the coffee shop at like 8 a.m. and I left about 8 p.m. I spent 12 hours in that one place. I did all the EAS reactions. And there's another benzene family that we don't teach you called NAS. But Beyonce's Lemonade had just come out, and I was listening to it on repeat for 12 hours while doing these reactions, so they're fundamentally associated. The reason I say this is because when we're talking about the relative naming on a benzene ring, if we have something on it, we can call it our R group. Right next door is ortho, O, then after that meta, then ops is para. The way I remember this, I think about romp. I imagine benzene in a little romper, listening to Lemonade by Beyonce, and benzene feeling really cute. Romp, R-O-M-P. This ortho-meta-para is a relative labeling system. It depends on where your R is. So if your R is over here, ortho is now over here. So what's the relationship between X and Y? Ortho. Y and W? X and Z. Okay, WZ. Nada. Great. Easy. So now, benzene and a carboxylic acid, we do a portmanteau benzoic acid. Is that okay? Now, if you have an OO bond, that's like a peroxide. So we call this peroxybenzoic acid. That okay? We added chlorine at the meta position. This is meta-chloro peroxybenzoic acid, MCPBA. Wow, there she is. When you first learned her, that meant nothing to you. But now, if I told you metachloroperoxybenzoic acid, you could build the structure, right? I love her. And just as a reminder, MCPBA, she takes an alkene to a what? An epoxide in a one-step fierce 5-arrow mechanism. Great. So, the whole thing with this section is, if we already have something on a benzene, how does that affect all these reactions? So there are two big questions that you need to ask if something is on the benzene. One, how does it affect activation? Does the thing that we add make the benzene more likely to do another reaction or less likely to do another reaction? And generally here we're talking about electron donating withdrawing groups. For the ES reactions, did we say that benzene was the nucleophile or the electrophile? It's the nucleophile, right? It's the one doing the attack. So if we have an electron donating group that's putting more electrons into the ring, do you think that that's going to make it a better nucleophile or a worse nucleophile? It has electrons, and if you're putting more electrons, you're making more electrons in your nucleophile that can go and attack something. So it makes it an even better nucleophile. Whereas if you have an electron withdrawing group, you're taking electrons out, you're making a worse nucleophile. And so electron donating groups activate the ring towards EAS, and electron withdrawing groups deactivate the ring. The second question after activation that we have to think about is direction. So it is based on where our group is, are we going to add to the ortho, meta, or the para position? And we call this directing effects. Directing effects are exclusively controlled by resonance. So we have kind of two big trends. The first one is electron donating groups are activating, which we already talked about, and they direct ortho and para. So if you take something like an amine here, and you draw out the resonance structures, what you're going to see is you're going to be passing around a negative charge to a bunch of carbons, and those carbons with a negative charge are at the ortho and para position. Those are kind of like hot spots of electrons, so if this ring is going to go and attack something, we are going to add ortho or para. We say that this electron donating group up here is an ortho-para director. It directs the next addition to be at the ortho or para position. Now, methyl groups, alkyl groups, are also electron donating via what? Not resonance, but hyperconjugation. Cool. Now, okay, also ortho-para direction, so which one? Give me an answer. Well, if you have a small R group, you're going to direct ortho primarily because it just outnumbers. It's like 2/3 ortho, 1/3 para. So that's okay, just math. But if you have a bulky R group, sterics is going to drive it to favor para over here if your R group is bulky. We never test you on this. Some classes do a lot with this, kind of like choosing which one's favored. For us, as long as it's ortho-para directing and you're trying to put it ortho or para, we're like, great. Cool. So electron donating groups are activating and direct ortho-para. Second key fact, electron withdrawing groups are deactivating and direct meta. So here, if you're taking electrons out of the ring via resonance, what you see is now actually a positive charge is being passed around at those ortho and para positions. So this is kind of weird to think about, but if these positions, ortho and para, are really electron poor, then the meta positions are, relatively speaking, going to be more electron rich. They are the ones who have not been robbed of electrons. And so, if you have an electron withdrawing group on the molecule, it is going to direct the next thing to be added meta, because that's what has the most electrons. Now, we can also, if we have something that can really strongly pull electrons out, because it's super electronegative, We can also withdraw via, what do we call this? Not resonance, but tugging electrons away. Induction. We're used to seeing induction with like a fluorine or something, like super electronegative element. But remember, a positive formal charge is just like ramping up the electronegativity on something. Also, compare her to NH2 over here. Can this NH3 plus do resonance? We're sp3 hybridized. We have 4 electron domains. We don't have a lone pair. So NH2 is an electron donating group, but sprinkle it in some acid, it becomes an electron withdrawing group. Crazy. You might see on the P side. Crazy. So electronegative atoms can withdraw via induction. The one thing that I have to say here as well for electron withdrawing groups is the nitro group and sulfonic acid groups are down here are so deactivating. They pull so much electron density out of the ring that it actually shuts down some reactions. Specifically, it's going to shut down Friedel-Crafts because Friedel-Crafts we said is finicky, right, with our carbon electrophiles. And so if you have a nitro group, you can add a bromine. You can add another nitro group. You can do several reactions. You can't add carbons. So this is like an important thing that often trips students up. I have made a ossified chart for you that shows this. All of our activators here are OP directors, and they are electron donating groups. We also see these electron withdrawing groups are meta directors, and they deactivate moderate or strongly. But then we have something weird over here with the halogens. The halogens are deactivating. They make the ring less reactive, but they still direct orthopara. What's going on? Well, they are electron withdrawing via induction, but they do have a lone pair, and they are donating via resonance. Is this good resonance? This resonance is not good, said with the tone of your love is not good. Exactly. Why is this bad resonance?
Because the more electronegative now has a positive charge and carbon has a negative.
I would go even further. The most electronegative element that we know, we've just placed a positive charge on that. Yikes. So normally we think about resonance being stronger than induction and hyperconjugation, but this is a case where the resonance is really, really weak. So in terms of which one's going to overall affect how the benzene reacts, the withdrawing is going to be the bigger effect. And so we say that it's deactivating. It makes the ring less likely to react again. However, directing effects are solely controlled by resonance. So even though this resonance is super weak, it is resonance. In resonance, it's donating. So we have it in OP director. And now for the sound cue. Fluorine, you are the only exception. Fluorine, good to see you. You're the only exception. My bro, bromine, you're the only exception. And what about me? I am the only exception. It's really nice because the chorus has the 4 and they're the 4 halides. But again, the driving point. Normally, electron donating groups are activating OP, withdrawing groups are meta and deactivating, except for the halides, which are deactivating in OP. That's the trend. That's it. Okay? Yeah.
One of the questions on the post-lecture quiz, it asks about the order that you would add a nitro group.
Yeah.
And then one that was Fe, a upper, I think it was bromine.
Yeah.
So if one of them directs meta and the other one directs orthopara, how do you know what order to go in? Especially given that nitro can't react with some of them. Is there do you
Yeah.
do the activator first and then
So
the
I have these boxes over here. I was going to draw a note to it later. But if you have multiple directing groups, ideally, they agree with each other. And if they agree with each other, great. That's exactly what you want. You want fewer side products. But if they disagree, whoever is more strongly activating wins.
Okay.
But we can talk about the
So do you-
specific
you
of
would
that
do
problem.
That one first, the one that's more strongly activated.
Yes, but we're going to kind of talk about this here. So we're going to do one example. So the hard part with these benzene reactions, line reactions, little mini syntheses, is not what is the reaction. If you see a acyl group, you know you've done Friedel-Crafts acylation. This, you know you've done nitration. This, you know you've done bromination. The hard part's figuring out the order. So I've listed out literally every potential order, and we're going to see which ones work and which ones don't. So I'm going to start at the bottom. If I start off by adding my acyl group first, is this going to be a orthopara or a meta director? So is she electron donating or withdrawing? That's the first question. Withdrawing, right? So she's a meta director. So she is supposed to direct here and here. Well, for our product, we have to add our bromine here. Is that going to work? No. Here, this would be trying to direct para. So this route does not work because our directing effects don't line up. Now, what if we did here for our nitro group? Is that meta to our carbonyl? Yeah, so okay, this works so far. But now I have my nitro group, I need to add this bromine. So I have my carbonyl here, which is meta directing over here. And I have my nitro group. Is nitro group orthopara or meta directing? Nitro group, electron withdrawing group, super strongly deactivating, it's going to be a meta director as well. So if I do this one as a meta director, is directing here. So both of them says the next thing has to add here. We want our bromine to add here. Does that work? No. So our directing effects don't work on this one. Okay. Now, what if we had our nitro group first? Well, then if we had our nitro group first, can we put on a Friedel-Crafts after our nitro group? This was the whole thing down here of some of our groups, nitro groups and sulfonic acid, are so deactivating, we shut down Friedel-Crafts. So we fully can't do either of these pathways. Here, we would fail because we would try to do Friedel-Crafts after nitro. And here we would fail for Friedel-Crafts after nitro.
And then I think on the P set there's like a tricky one with that because they add the PR directly to the ring, like not on a carbon.
Yeah, I bet there is a tricky one like that.
Okay.
Okay, and then between these two, let's start off with bromine. Is it electron donating or withdrawing group? So this is the whole thing. It's an electron withdrawing group. It's a deactivator. But then my question was going to be like, okay, electron withdrawing group, is it a meta director? No, it's the only exception. So our bromine's going to be orthopara directing. So it's going to direct here and here. Okay, well, would this NO2 be directed to one of the orthopara positions? Yeah, that works. Would this one be directed to one of the orthopara positions? Yeah, so that works. But then this top one, you're doing Friedel-Crafts after nitro. That doesn't work. And so for this one, the only one that actually works down here, this one's a meta director, so it's going to be directing here. And then the bromine is an orthopara director. So it's going to direct here. Here, the directing effects agree. And hey, do we add the nitro group to one of those positions? Yes. This is the only route of these 6 literal potential combinations at all that can work with directing effects. And this is where the strategy and the thinking of these EAS reactions really comes into play.
Do you ever have multiple options though?
Sometimes. Bring me the question afterwards, we can talk. But, cool. Normally at this point, I would be like, okay, now let's work on some practice of the benzene and get with everything. But I do think it'll be more helpful to do synthesis and high-study reactions part 3. So, any other EAS reactions or anything on lecture 9 before we close that chapter? Slide. Okay. What's the transition? What do we do? No. Welcome back to How to Study Reactions, Part 3. How to study reactions part 1 was, what are reactions? What do we look at? How to study reactions part 2 was, okay, how do we get to where we can execute reactions really quickly once we have a reaction in mind? That was our desert island drill. How to study reactions part 3 is like, okay, the exam's coming up next week. Let's talk about what the challenge is. The challenge for exam 1 was, you've never seen molecules, respectfully. It was a lot of different skills and just like, what are reaction problems? The challenge of exam 2 is very different. It is one challenge, and it's, you now have 80 reactions. So, looking at the question outline from the exam, this is historical, this is probably what we're going to do this year, this is what the practice exams are. 3 pages of box problems. 1 of those pages will be substitution and elimination. 2 pages of synthesis, 2 mechanisms, and 2 pages that are theory, reactivity, miscellaneous mechanism kind of things. So things that this has been historically, which are the fastest of SN1 and SN2 reaction, where we give you 3 molecules and we're like, okay, what's the fastest SN1? Something like that. We have like CAD reactivity. Is an acid anhydride more reactive than an amide or less? We have a bunch of page 9, or lecture 9 things. We have aromaticity. Give you a molecule. Is it aromatic, anti-aromatic, non-aromatic? We have directing effects. We have, is it activating or deactivating? What we were just talking about with EAS stuff. We can do things with like carbocation rearrangement. This is kind of what's immediately coming to mind. You'll see examples of this on the PSET. But those 2 pages, hopefully, will be the easiest points of the exam. Most of the questions that we are going to be asking on these pages are like for you to fill in a bubble. And so hopefully also those are the pages that you can save a little bit of time on, and for these skills be kind of locked and loaded and have those trends all like memorized and kind of ingrained. So one thing I want to plug out, 7 of 9 questions are reaction based, and 5 of the 9 are at the line reaction level. They are box problems and synthesis. Only 2 of the pages are mechanisms. So you do need to know the mechanisms. Yes, the desert island drill is great for the mechanisms, but we need some more tools for really, really building not only just like basic memory, but fluency at the line reaction level. So I'm going to introduce a few more strategies to study at that line reaction level. But before I do that, quick timeline things. Your number 1 goal right now should be to finish PSET 5 as quickly as humanly possible. I would say try to be done with it, or like 90% done by like Friday night, so that you can spend Sunday and Monday doing your studying of reactions, doing your desert island drills, and doing some of these exercises that we are about to talk about. Then after that, Tuesday and Wednesday are going to be your heavy practice days with the practice exams. I'm going to send an announcement out about like how to approach them. I would still save 2 of them to do under timed conditions like we described in that first scary message. The other 2 you can also do timed conditions, but it's from when the exams were 2 hours long, and so there are like 12 questions, so it's a little bit different in format. It might be more useful to deconstruct those and be like, I'm going to work synthesis now, and then I'm going to work mechanism now, and then I'm going to work box problems, that kind of stuff. Also, you only have solution videos for the 2 posted, the ones that we give you printed copies of. So, strategies. Before I do that, one more thing. Something you're studying has to engage with 2 challenges. The first one is tractability. Right now, these are like a long laundry list of reactions and like 100 or 200 pages of lecture notes, which is crazy. So if you're trying to do those like in a sequence, memorizing 85 things in a row, that's just not going to work, and it's going to be overwhelming. So something you're studying needs to grapple with this and organize it and compartmentalize it. My preferred way of doing this is dealing with reaction families. So you have about 14 reaction families for this entire course. I like to think about them as the drawers that we're putting all the reactions in. But even within this, go to the container store, get more drawers. Within redox line reactions, you have your oxidations and you have your reductions. Within oxidations, you have your pure sidekick ones and you have your H2O sidekick one. Within your reductions, you have your ones that make amines and you have your ones that don't. Within ethers, you have your SN1 style, you have your SN2 style with the Williamson ether, and you have your alkene sneaky ones. Like, really try to build a schema, a mental organization of these. And the one warning I will give you is if you are making some sort of study sheet for this, do not make it pretty and do not make it comprehensive. If you are spending many, many hours making the sheet to compartmentalize, those are hours where you are not ingraining these reactions to be able to do the execution of it. So just be really watchful for that. Like, the way I would organize these is instead of even doing full line reactions, just be like, oh, the Grignard. Like, think about them as kind of a concept, and you are organizing the concepts together. But the other issue is right now, y'all are really good at being like, I'm in lecture 9 mode. Okay, EAS. I'm in lecture 6 mode. Substitution elimination. But we need to get you to ping pong between all of them, because a good synthesis, my benchmark for writing a good synthesis is a synthesis that covers at least 5 of the lectures. 4 or 5, maybe. So we need to think between them. And these strategies, I think, will help. So first one, we're going to go on a chemical nature walk. We're going to touch grass. We're not actually going to touch grass. So start off with a small molecule. And I'm just going to be like, what can I turn that into? I don't know. Let's make it a bromine. What reagent should I use? What? Yeah, PBr3, great. Okay, now I'm a bromine. Ooh, okay, I have a good leaving group, so I'm gonna add nitrile. Sneaky little nitrile. And then nitriles. I don't really know many reactions of nitriles. But I can go in CAD now, and I can go to a carboxylic acid, you know? And again, we have no particular goal in mind. We're just going to kind of see where it takes us and see, okay, can I try to like mix it up? Can I do something different, you know? So now we're carboxylic acid. And what reagent do I need for that?
Do acid or base.
Only acid, H3O+. Oh, no, you're right. You can do acid or base. You can only do acid for amide hydrolysis. My bad. So then I'm like, okay, maybe I want to leave CADland. What if I made an alcohol? Okay, well that would be like using lithium hydride. And then H+ workup. Or actually, wait, I didn't want to leave CADland. What if instead I wanted to make an amide? What could I do for that? Well, I could use DCC. And then if I'm adding just NH2, I put NH3 here. Now from an amide, I don't know. Where could I go from an amide? I could reduce an amide. Like this thing. I know it feels kind of frivolous, and I know it might feel like a waste of time. For me, it's a great warm-up. Because the thing that's really frustrating is when you know you can transform it from one functional group into this other one, but you're forgetting the reagents. Or if you want to be like, okay, what would happen if I added an AOH to this? The answer is nothing, but you would have to think about that and figure it out. Like, I think it puts you in a space right now, a lot of you are in a fear space of reactions, and this puts you in more of like an open Zen space, creative space. So I like a nature walk as a warm-up, especially before a study session. Next question. Do you have friends?
Wait, we're supposed to make friends?
Do you have friends? Hopefully one's in this class. If so, I think that you should message them today and say, hey girlies, hey besties, let's do a synthesis potluck. So what you do is you say, okay, on Monday we're going to meet, or we are going to digitally swap things. And everyone comes and they have prepared a home-cooked synthesis. Maybe one synthesis, maybe 2 synthesis, go crazy. When you do that, make an answer key for your synthesis and make a blank version. And then you swap, and suddenly you have tailored, curated syntheses for this class, which are rare to come by because you're not really going to find any online. It's all idiosyncratic based on the set of reactions in each class and like the order that they are taught, and no one else teaches it this way. So I think that it's a great exercise, one, to put you in the mindset of me making it. Be like, okay, can I write a synthesis where I go between a bunch of reactions? 2, be mean to your friends. Try to write a hard synthesis that you're like, Joseph, I'm gonna stump you with this synthesis. You know, you're never gonna figure it out. Like, do that with your friends. Be mean, because it makes you think in more complicated ways as well. And also because it's going to be really embarrassing if you try to make a hard synthesis and it doesn't work and it's wrong. Your answer key is wrong. So again, all of these are exercises to get you thinking about these and making it so that there's something other than a fear response on the exam, and then you leave the question blank. I've left many a synthesis question blank. You know, no judgment. Synthesis potluck, friend syntheses. Last strategy are reaction webs. And, you know, a reaction web here is you put a functional group in the middle, and you ask, what are all the ways that I can make this functional group? And what are all the things I can do with the functional group? And when you are starting to fill this in, it's going to take a long time to figure out what are all the things in and out. You're going to have to kind of go through your lecture notes and everything. But once you've made a web for the first time, then you can erase the reagents, you can erase the products, and then you can start to do it in a timed way. So go ahead. Oh, you're just, yeah. So this is one I would normally do with you and be like, okay, what are all the ways that we can make alcohols, whatever. But because I had a diversion earlier, I'm going to do it as a test for me. So like I said, you do it the first time and it takes you a long time, but then erase it and then set a timer and see how quickly you can fill it in. So does someone want to time me?
Sure. Okay. 3, 2, 1, go.
Okay, I can make alcohols from a carboxylic acid or from an aldehyde. I'm going to cheat a little bit and put LAH for the reduction conditions, but I know that I can get the full ones from that. How else can I make an alcohol? I can make it from an alkane with like H3O plus, or I could use hydroboration oxidation, but it doesn't really make sense for this alkene. I start off with an alcohol. What else can I do with it? I can make it leave. I can make it a chlorine. I can make it a bromine. I can make it a tosyl. So these are kind of leaving group situations. So I use Succal 2, I use PBr3, I use TSCl. Okay, what else can I do with an alcohol? I can turn it back into a carboxylic acid. That's kind of silly. Or an aldehyde. So these are our chromium boys. And then if I'm going to carboxylic acid, I need a cyclic of water. And then I use pyridine over here. So aldehyde, carboxylic acid. I'm labeling these functional groups as I go because, again, the functional group transformation is important. Now the weirdish ones. Okay, alcohols. They're involved in like acetal stuff, right? So like acetal. So I would need a carbonyl. I would need H plus acetal. Okay. Ooh, I could make an alkene. I could do kind of like a E1CB, ooh, but no, I can't do that with a primary alcohol, right? Because that would be a primary carbocation, so that doesn't work. Shoot. Okay, alcohols, what else can they do? I can make it into an ester, right? And for that, I would need like a carboxylic acid and H+. What's the last thing? Well, it's kind of turn an alcohol into, oh no.
We don't know.
I'm gonna cheat. I have time. What was it? Oh gosh. Ether. It was 1 NaH, 2 like ethyl bromine.
That's funny.
Ether. But again, do you see how that's going to be helpful? Like, do you see how once you find all of them, being like, if I have an alcohol in a synthesis, I want to be able to quickly brainstorm all the things I can turn it into. This is hard. It's a test because you're doing all the reagents and everything. But just to be like, okay, what are the families of things I could turn it into? I could do leaving group stuff. I could do oxidation stuff. I can do some like alcohols that normally belong on the arrows. But like, it's the gold standard for studying for Bach problems in synthesis. The gold standard. And so do this with a bunch of functional groups, as many as you can think of. Divide them up with your friends. You take some, they take the others, you build them together, and then you do time trials of like racing and filling them in. Yeah. with our last 10 minutes, because I went 5 minutes over, or I started 5 minutes late, are we ready to talk about our synthesis? Are there other questions for how to study reactions? Yeah, Josie.
Does that whole list like cover everything that we should be doing
No.
notes for?
There's a ... and many more. And many more.
And we'll just find them by like we can do all the reactions.
Yeah, kind of just like thinking, what are all the functional groups I know? You can do it for everything. Some of them are going to be small, like amine. There's one reaction that makes it.
Yeah.
Yeah. So now you know how to study reactions. Yay. Thank you for coming to my 3-part TED Talk. This is a hard synthesis. It's a pretty hard synthesis. It's a stinker. 11 or fewer steps. Woo! Woo! Just initial vibes on this. Yikes. The initial vibe is yikes. I want you to spend 90 seconds doing your initial brainstorming, ID functional groups, maybe kind of brainstorm some reactions connected to them. And then the other thing that I want you to do is I want you to think about how many carbons we have in the starting material and the products. You have 90 seconds. Okay. So, starting material, I counted there were 6 carbons. I'm clocking the alkene, I'm clocking the ring. In the products, I'm clocking that there are 8 carbons. So somehow we've added 2 carbons. Eep. And we have primary amines. And also, no ring. Eep. Okay. Well, I kind of gypped you when we were doing the brainstorming here, because I was going to be like, oh, what are the ways of making primary amines? And it's going to be fresh in your head. And there are only 2 ways that we can make primary amines in our class. We can either make it from a nitrile that we do a reduction on, or an amide that we do a reduction on. So again, if we have those kind of functional groups brainstormed, these are the only 2 places it could have come from. So I've just drawn these out as kind of potential targets. But let's start to think about the kind of main issues in this synthesis that we need to do. So first issue is probably the biggest one, is we need to add 2 carbons. We said last time that we did long synthesis that that's going to be a core challenge in organic chemistry, and we only know a few ways to make carbon-carbon bonds. What are some ways? Yeah, we can do Grignards. What else? Grignards or other like organometallics. The Vidic, great. What else? That's in the kind of Grignard camp family. Yeah. Might not be the most relevant here, but we talked about adding carbons to a benzene today. What was that called? Friedel-Crafts. Okay. One more. We can do an SN2 with cyanide. With cyanide, CN minus, doing an SN2 attack, because that's a carbon nucleophile attacking a carbon electrophile for an alkyl halide. So these are kind of our main options for adding carbons. Our second issue is to open a ring. So the way I used to have of remembering this is kind of inappropriate. But I do think that if I say the inappropriate thing, you'll remember it. Is that okay?
Yeah.
Okay. So ozonolysis, you know, she's the one with oxygen scissors. When we had the alkene on the ring, we busted it open. I used to earnestly refer to ozonolysis as the Lord split me open reaction because I thought that that was a genuine term used in a religious setting. I thought it was like, wow, I found the light and like it opened up my world. And I thought that people made bad jokes online with that phrase. Turns out, not used in religion at all. Yes, so not really applying here. But if I need to bust open a ring, I'm thinking Lord split me open ozonolysis. So sorry. Ozonolysis. And so for ozonolysis, we need to get an alkene on a ring. Hypothetically, we could use radicals, but again, we want to avoid radical stuff as much as possible in synthesis. Okay, and then the third issue is adding nitrogens. So already, just with our brainstorm here, which route do you think we want to use for adding carbon-carbons? Is there something that would be 2 birds, 1 stone? Yeah. If we do our SN2 with nitrile, we add the nitrogens through this route. So, again, it's kind of just seeing what are our options, and based on our goals, that can kind of limit us in a way that will be helpful. So I'm going to go ahead and say this is our last step. And I'm going to write 1 lithium aluminum hydride, Et2O, and 2 H plus workup. So that is what we use for the amines. For the nitrile reductions. And then, if I'm thinking backwards again, I know that this came from SN2, so I'm going to put a leaving group. I'm just going to put a bromine, for lack of a better thing right now. Cool. So then I would do NaCN, and that would do like an SN2 attack here. So I already have my last 3 steps, so that should be good. So now, let's focus on busting open this ring. So now, we need to get an alkene in the ring in order to do ozonolysis. So how do we make an alkene? Like E1, E2, right? And so we need a leaving group, but we're starting at an alkene just in the wrong spot. So what we need to do is install a leaving group and then make a different alkene. So maybe let's think about, okay, how can I get a leaving group added when I start with an alkene? Give me an example of a leaving group.
Chlorine.
Bromine, chlorine. How could I add a bromine close to the ring over here? That adds 2 bromines. HBr. Let's try that. HBr, it adds a bromine Markovnikov towards the ring, right? So that seems like it would get in the right place. And I could go put a bromine. I've fallen into a trap. What trap did I fall into? This reaction proceeds through a carbocation. And anytime you're doing a reaction that proceeds through a carbocation, you need to draw out that intermediate and check for a rearrangement. Can this rearrange? We're going to do a ring expansion. Can this carbocation rearrange?
Yes.
Can this carbocation rearrange? Thank God. So we're not going to get that product. Boop. I'm going to keep it there but do red. Instead, we are going to get 5-membered ring, and we add our bromine here. Okay, like our ring got bigger. That doesn't seem to matter. We're going to break it open anyway. And so now, what do we need to do an elimination that would put our alkene in the ring? To an E2 elimination, what do we need? A base. Give me a base. Say again?
NaOH.
Sure, NaOH. I'm biased. I'm going to use my favorite. I'm going to use Naomi. Could I use Cotbu?
Yeah.
Yeah.
Cotbu's bulky. Cotbu would make that alkene. Remember, Cotbu we use to make less substituted alkenes. If we want to use Zaitsev's rule and make our more substituted, which this is the one that we do want, then we want to use a smaller base. Cool. Okay, ready to split it open? Let's use ozonolysis, and I'm just going to choose reductive conditions. I can probably do it either way. So when I do this, I pop a carbonyl onto both sides, and we get this. Now let's see how this lines up with our product. Like here we had a 1, 2, 3, 4, 5, 6. Now we have a 1, 2, 3, 4, 5, 6 chain. Okay, great. I'm just going to redraw this to look similar. Okay. So now our transformation is we need to get from a ketone aldehyde to an alkyl halide. It seems like we are at the wrong oxidation level, right? We're in oxidation level 2 for ketone aldehyde, and we're 1 for the alkyl halides. So let's do a reduction. NaBH4 MeOH. Okay. Can I turn alcohols into bromines directly? Hell yeah. What do we use? We're done. So, this is tricky. Like, we are doing these weird transformations where now molecules are opening up. We are making these amines and like long chains. We're adding carbons. But our strategy kind of stayed the same. Our strategy was we analyzed the starting materials, product, functional groups. We brainstormed things that were closely related to it. We identified what are the issues our synthesis needs to do. And as we were thinking through that, we came up with our first strategy. We started working from the end. We were working backwards. And then once we addressed that goal, adding the N, the CNs, then we focused on the opening ring. This one, it took us in some unexpected places with the rearrangements. But again, do you see how like all of this is like what functional groups do we need to transform into? Where do we need to put them? And kind of it's trial and error. And the faster you can get at like what are the tools in my arsenal, the better you're going to be at synthesis. So thank you for coming to section number 9, our penultimate section. Please get rest this weekend. Take care of yourselves. Study hard and hearty, and we will see you at Help Room on Monday. Goodbye.